Good evening, everyone. First of all, I would like to thank the organizing committee for inviting me to give a talk on room temperature ferromagnetism and phenomena in 2D generation metal diagonalized. Two-dimensional van der Waals materials, especially 2D generation metal diagonalized, are of great interest as building blocks for many modern flexible, ultra-fast, and ultra-thin nano devices. It's my great honor to have met and discussed with the world-leading scientists in the field of 2D materials and magnetism, and their work has inspired and motivated us towards the discoveries of new 2D magnets that have the potential to transform the field of quantum spintronics and quantum computing. Historically, the 2D magnetism was established in 1944 when Onsager predicted the existence of long-range order in a 2D Ising magnet. However, according to the Hohenberg-Mermin-Wiener theorem, no order possible in 2D Heisenberg magnetic system. Research on 2D magnetism only became booming after the discovery of intrinsic magnetic long-range order in chromium iodide and chromium germanium telluride in 2D limit in 2017. These 2D magnets are a source of fascinating fundamental physical phenomena, but they do require cryogenic temperatures, protection from the air, and a modest external field to induce magnetization. Our discovery of strong room temperature ferromagnetism in monolayer palladium diselenide in 2018 has triggered global attention. However, these magnetic monolayer are metallic, which cannot access the rich electrolytes and optical phenomena open to semiconductors. Practical application of 2D magnetism will likely require room temperature operation, air stability, and the ability to achieve optimal doping level in magnetic semiconductors without dopant cluttering. To this end, we have discovered strong and tunable room temperature ferromagnetism in semiconducting monolayer palladium-doped tungsten disulfide and palladium-doped tungsten diselenide. In this talk, I will present our new findings in this 2D system. First, let me talk about our discovery of room temperature ferromagnetism in monolayer VSE2, which has already received a great deal of attention and stimulated a lot of study during the last 2 years. Let me recall the DFT calculation performed by Ma and colleagues who predicts the room temperature ferromagnetic order in monolayer VSE2 and related compounds. They predicted that this monolayer possesses in-plane spin alignment and attribute the origin of ferromagnetism to the combined effect of through bond and through space interaction, which both depend sensitively on strain. A later DFT calculation shows that the Tc of this monolayer is about 450 K. To testify this prediction, we use monolayer, binaire and multilayer film VSE2 on graphite and on MOS2 substrate using MB methods. We find that monolayer VSE2 can be better grown on MOS2 substrate. From scanning tunneling microscope study, we observed a gap openings at low temperature, which is a result of the charge density wave transition that occur around 115 K, which is also observed in the bulk vanadium dicyanide. This is also consistent with a sharp increase in electrical resistance below this temperature. Having characterized magnetic properties of this monolayer, we find that the monolayer VSE2 grow on graphite LPZ show a strong ferromagnetism and above room temperature, which is independently confirmed by vibrating sample magnetometer and magneto-optical effect. So in-plane and out-plane magnetic resistance loop measurement indicate the presence of the in-plane magnetic anisotropy, which is in full agreement with the DFT prediction. The temperature dependent of saturation magnetization and corrosive field indicates variation around 115 K, which is associated with charge density wave transition. A comparative study of logically dependent magnetic properties shows that the strong magnetism is only achieved as a single layer limit. Room temperature ferromagnetism is further confirmed in monolayer BSE2 grow on MOF2 substrate. In this case, the enhanced magnetization and corrosive field and the strong temperature dependence are observed. Given the fact that MOS2 exhibits weak ferromagnetic ordering induced by vacancy effects, the growth of magnetic monolayer VSE2 on it could promote magnetic exchange coupling and enhance the ordering of the magnetic moment in MOS2 layer due to magnetic proximity effect. This could give rise to the enhanced magnetism in this particular system. We also determine the pre-temperature of this monolayer by fitting the temperature dependent of saturation magnetization to block equation at high temperature, which give a value of 430 K. This TC value is close to that predicted by DFT calculation. The strong magnetic interface coupling between VSE2 and MOF2 layer has to discover a tunable exchange-based effect in this heterostructure. In particular, magnetic hysteresis loop measurements in fin-cooled and zero fin-cooled regime confirm the shifts in the negative magnetic field direction, indicating the exchange bias in this system, which is absent in the monolayer VSE2 grow on graphite or on hexagonal boron nitride. The exchange bias effect show a large enhancement at low temperature, which is below 50 K, that could be associated with the occurrence of long-range magnetic order in MOF2 and due to magnetic field enhanced interfacial coupling between VSE2 and MOS2. The exchange bias field can be optimized by changing the cooling fields that you see from here. Furthermore, we demonstrate the possibility of tuning exchange bias field by changing magnetization of the monolayer PSE2 or by changing the size of PSE2 magnetic island or the coverage here. Now let me present our latest finding on the tunable room temperature ferromagnetism in semiconducting monolayer palladium doped tungsten disulfide and tungsten diselenide. A promising approach to induce long-range ferromagnetism in TMDs is by introducing magnetic dopants to form a dilute magnetic semiconductor. Recent efforts has been devoted to achieving this goal. However, creating the dilute magnetic semiconductor without dopant cluttering and phase separation represent one of the more challenging issues in the 2D material synthesis. Using advanced CVD techniques, we have now overcome the challenges and demonstrate for the first time that we can not only induce ferromagnetic O-ring at room temperature, but also enhance and tune the ferromagnetism in palladium-doped TMD monolayer system over a wide range of doping concentration up to 10%. The TM and VSM data consistently shows that the saturation, magnetization, and coercive field can be enhanced and optimized by changing palladium concentration. The 2% sample show an optimal magnetic responses. Using a Bloch's law methods, we can determine the critical temperature of 470 K for this monolayer. By studying the palladium concentration-dependent Bloch coefficient, we reveal a transition from short-range to a long-range ferromagnetic order when palladium concentration exceeds the critical concentration value. Details on this study will be presented in my student poster at the notice here. To complement the experimental observation, we have performed DFT calculation using two different approaches. The first model shows a ferromagnetic coupling between VV nearest distances and anti-ferromagnetic coupling at further VV distances. The second model shows a ferromagnetic coupling between V and W side as nearest and further distant. This calculation accounts for the existence of an optimal magnetization at a certain dopant concentration above which ferromagnetism is quenched due to the orbital hybridization at the two close palladium distances. For monolayer palladium-doped tungsten diselenide, we observe the uniform dopant distribution from the edge to the center of W82 flex as compared to palladium-doped tungsten disulfide monolayer. TM, AFM, MFM study indicates the absence of magnetic domain or magnetic O-ring in pristine W82s, but the clear magnetic domain in V-doped W82 sample. The magnetic domain disappears in highly doped samples such as 8% as we show here. These observations are fully consistent with the magnetic data that shows the ferromagnetism above room temperature in this monolayer, with the 4% doped sample showing an optimal magnetic response, which is the highest doping level ever achieved for vanadium-doped TMD monolayer. The observed ferromagnetism in this system can also be explained by the theoretical model used for the vanadium-doped W82 WF2 monolayer. However, the DFT calculation reveals the anti-ferromagnetic coupling between the magnetic moments of vanadium and tungsten side at nearest distance, but the ferromagnetic coupling for VW at the further distance. This unique feature is different from that observed in vanadium-doped tungsten disulfide monolayer. It is the presence of the weak anti-ferromagnetic coupling between the V and W magnetic moment at a near distance that leads to the observation of novel thermally induced spin flipping effect, which occur at low field as a crossover seen in magnetic Higgs loop here. At high temperature above 175 K. Very interestingly, the thermally induced spin flipping effect can be manipulated by changing vanadium concentration within the tungsten dicyanide monolayer. The discovery of these effects could enable the high performance of spintronic nanodevices. The coexistence of ferromagnetic and anti-ferromagnetic interaction and magnetic exchange coupling in this system is further confirmed from the chaining effect study. Having discovery of the tunable room temperature ferromagnetism in this vanadium-doped TMD monolayer, we ask ourselves a question: can we manipulate and control the 2D magnetism at room temperature with the external stimuli? In this presentation, I will show you how we can manipulate and control the room temperature ferromagnetism in vanadium-doped tungsten disulfide monolayer with the laser light. To do so, we develop a novel measurement system that combines the advantage of LC resonance with the giant magnitude impedance effects. In principle, the change in magnetic stray field from the monolayer subject to the laser radiation can be precisely tracked by the change in its magnetic reactance, which is proportional to the magnetic permeability of the monolayer. We find that the present WF2 monolayer does not show any magnetic response to the laser light radiation, while the light radiations increase magnetization of the V-doped WF2 monolayer. The magnetization can be tuned by changing the laser intensity, as we can see from here, it starts increasing and becomes saturated at the highest laser intensity. Guided by the DFT calculation, we attribute this phenomena to the presence of excess holes in the conduction and valence bands, as well as carrier charges in the magnetic doping state, which in turn mediates the magnetization of vanadium-doped tungsten disulfide. For the detailed discussion on the important finding, I would refer you to my student oral presentation as noticed here. Using another novel approach, we demonstrate the light control of room temperature ferromagnetism in a novel heterostructure that consists of monolayer BSE2 and a monolayer or bilayer MOF2 grow on silicon dioxide substrate using the combined CVD and MBB methods. Our scaling nitrogen vacancy spin magnetometry shows that the presence of magnetic PSE2 layer enhance the magnetization of the MOF2 layer and enable the controllable manipulation of magnetization of this heterostructure when exposed to light. That we can see from here. This magneto-LC resonance and magneto-optical effects experiment clearly indicates the increase in magnetization with laser intensity and tend to saturate at higher laser intensity that we also observe in FIDO W at 2 monolayer. Our study opened a new path to the light control ferromagnetism in two-dimensional TMD heterostructure-based spintronic nanodevices. In addition to the fundamental novel phenomena they exhibit, this monolayer has recently been explored as a novel magnetic sensing element for making highly sensitive magnetic sensor. To summarize, we have discovered the strong and tunable room temperature ferromagnetism in monolayer PSE2 and semiconducting monolayer P-doped WS2 and WSE2. We have also discovered the tunable exchange bias effect in VSE2 MOS2 heterostructure and demonstrate for the first time the light control ferromagnetism in 2D TMD system, including V-doped WS2 monolayer and VSE2 MOS2 heterostructure. To fully understand the origins of ferromagnetism in 2D TMD and heterostructure, we must study the role of transition metal and jargons, dimensionality, quantum confinements, surface and interface effects. It's also very important to decouple intrinsic magnetism from effective magnetism in this 2D system. It's anticipated that the room temperature 2D magnets and their heterostructure are the novel building block for many new generation devices application in spintronics, opto-spin caloritronics, electronics, and quantum computation. All of this important work could not be as accomplished without significant contribution from all my former and current students and postdocs, as well as our collaborator and as group member. With this, I wish to end my presentation and thank you for your attention. I would be more than happy to address any question or comments you may have. And here, the list of other presentations from my group.